my name is Shaukat and I'm here to present this paper titled as Do Quality Indicators Prefer Particular Multi-Objective Search Algorithms in Search-Based Software Engineering. This work is in collaboration with my colleague Paolo Arcaini from National Institute of Informatics in Japan and my colleague Tao Yue from Similar Research Lab in Norway and also from Nanjing University of Aeronautics and Astronautics. So first I will present briefly the outline of my talk. I will start with presenting some background and motivation of this work. Then I will present our empirical evaluation including research question, experiment design and settings and results, and then I will present some key discussion. Finally, I will conclude the talk and present future works. So let's start with background and motivation. So in the context of search-based software engineering, we find that many problems that we want to solve are multi-objective by nature. So this means that when we have to solve a problem, we need to select a particular multi-objective search algorithm to solve the problem. So the question is, which multi-objective search algorithm or MOSA I should use to solve my problem? And if you look into the literature, you will find that usually people don't provide any justification of selecting one or more multi-objective search algorithms. And another common justification, you will find that people selected the most popular algorithm. And if you look at the literature, you will find that the most popular algorithm is NSGA2. So the motivation of this work is that can we provide a better justification of choosing a MOSA based on some evidence? And we know that a typical practice is that when we want to select a particular MOSA for a problem, what we do is that we perform large-scale experiment. So we select 5 or 6 different algorithms, then we run large-scale experiment, and then we select one or more quality indicators, and then based on quality indicator we compare pair of algorithms, and then we select the best algorithm based on a particular QI that give me the best results. So instead of doing all those large-scale experiments, can I know which algorithm will be preferred by a QI, or one or more algorithms actually can be preferred by QI, so that I can just select those MOSAs to perform experiments instead of selecting several different algorithms. So our approach is empirical evaluation, and we believe that some of this work can also be done based on some theoretical analysis, but we don't find ourselves experts in theoretical analysis, so that's why we wanted to do some empirical evaluation to come up with some results. So the key idea of our work is based on checking preferences of QIs for MOSAs, and we do so by empirically studying the relationship among different quality indicators and MOSAs that have been used in the context of search-based software engineering. So our ultimate aim is to guide SBSE users in choosing MOSAs that represents the solutions measured by a specific QI. So typically, when I'm solving a problem, I know what kind of characteristics I'm looking into the solutions that can be represented by a QI, or that is a quality indicator. So it means that if I know, I should be able to help users to choose a MOSA for my particular case. So let's go to empirical evaluation. So we wanted to address two key research questions. The first question is how frequently a quality indicator prefers a particular MOSA. So in this case, we are ignoring the differences between different search-based software engineering problems that we studied, and we want to study the results at a high level. Research question 2. How frequently a QI prefers a particular MOSA across the different SBSE problems? In RQ2, the key difference is that we want to take into consideration SBSE problems. We will not merge all the data from all the problems, but we analyze the data problem by problems. So here is the design of our experiment. So before going to present the design of the experiment, I'm going to present a very important concept that is required in our empirical evaluation. So it's called preference relationships. So how do we define the preference relationship? So let's say we have a multi-objective search algorithm A and another multi-objective search algorithm B, And we say that if A is significantly better than B in terms of a particular QI, for example HV, then we say that the QI prefers A. And when we say that A is significantly better, it means that we study the statistical significance based on the relevant test, for example Mann-Whitney test and A12 to study the effect size. So here are the different steps in our experiment. Step 1, we execute all MOSAS on all our SBSE problems. Second step, we calculate quality indicators such as HV, epsilon, and so on based on the results. And step 3, we compare each pair of MOSA based on pairwise comparison using each QI. So for example, if I have an SGA2 and SPR2, we compare it with HV, epsilon, and all the selected quality indicators with statistical tests such as Mann-Whitney U test. And then based on step 3, we go to step 4, step 5.1, and step 5.2. And here I would like to mention that step 1, step 2, step 3 were performed in our previous work. And we just use the data in this paper to perform step 4 and step 5.1 and step 5.2. In step 4, which is about answering RQ1, we study the preference counts to answer our research question 1. In step 5.1, we compute preference count per problem for each MOSA, QI, and problem. So the difference is that in RQ1, we ignored the problems. We studied all the data together. In RQ2, we are studying preference count per problem for each MOSA, QI, and problem. And then in step 5.2, we are studying pairwise comparisons between MOSAs for each QI across all the problems. So in 5.2, the key difference is that we pick a pair of algorithm and we perform statistical tests to compare them across all the problems. And the statistical tests that we used were Mann-Whitney U test, and effect size was measured with A12 statistics. So this is, here I'm going to quickly list the problems, case studies, and MOSAs and QIs that we used for empirical evaluation. So we used 3 different categories of SBSE problem: industrial, real world, and open source. In industrial, we studied test suite minimization, prioritization, and rule mining and configuration generation. And I like to mention that these were the industrial case studies that we have access to at our lab. And so we have the real data available or from the real systems. And here in the case studies column, you can see that how many systems that we had corresponding to each SBSE problems. And then the last column shows the number of objectives that were in each problem. For example, you can see that in case of test suite minimization, we had just one system, and the problem had 4 objectives to optimize. But if you look at, for example, test case prioritization 2 problem, you can see that we had 3 different systems for prioritization, and the problem that we solved had 2 objectives. And then we selected these multi-objective search algorithms to perform our empirical evaluations. And these are the list of QIs that we chose to study in our empirical evaluations. And these were the ones that we found in the literature that were used in SBSE literature. Similarly, these MOSA were commonly used in SBSE literature. So now let's go towards the results for the research question. First, RQ1. Just to recall that we are studying how frequently a QI prefers a particular MOSA. So this is the table that summarizes the results for each quality indicator, and for each multi-objective, what was the preference count. So here you can see that, for example, for HV quality indicator, NSGA2 was preferred 75.93% of the time. When we look at another quality indicator, IGD, we can see that NSGA2 was preferred 77.78%. And now, for example, if we look at quality indicator C, we can see that SPR2 has the highest preference, and PAES has was the lowest preferred by C. But in general, you can see that for C, the preferred percentage is quite low. And if we look across different table, we can see that PAES was never preferred by any quality indicator in general. And then we look our results from another perspective. So here you can see that we present different graphs for each quality indicator: HV, IGD, EP, GD, and so on. And here you can see that we present the result in a little bit more different way. And you can see that in most of the cases, when you look around, you can see that SPR2 and SGA2 will be the top in their top two positions because they were more preferred by most of the QIs. And of course, there is exception. For example, if you look at GS, SMPSO was the most preferred one, followed by CELDE. Now coming towards our results for research question 2. So in research question 2, we wanted to see how frequently a QI prefers a particular MOSA across different SBSE problems. It means that we are also considering each SBSE problem in this analysis. So here we present the summarized results, and when we studied these MOSAs, so as I mentioned before that we did statistical tests. So for example, each number in a cell here shows number of times each algorithm was preferred by a quality indicator over other studied MOSAs. For example, if you look at this, you can see that if you look at the first row, we can see that uh, when we have quality indicator C, NSGA2 has number 2. It means that in terms of C, NSGA2 was significantly preferred over two other multi-objective algorithms. And if you look in general in the table, you can see that the results, the numbers for NSGA2 are the highest, and these numbers are actually quite similar to SPR2 as well. For example, you can see that these numbers most of the time are the same except for HV, where MOSA, that is NSGA2, has number 3, whereas SPR has number 2. And also there's a difference in terms of PFS, where NSGA2 was preferred 4 times, whereas our 4 algorithms, whereas SPR2 was preferred in our 3 other algorithms. So the results are quite similar for NSGA2 and SPR2. And this observation is quite similar to what we saw in the graphs in the last slide, that NSGA and SPA2 was the most, or were always on the top 2 position in terms of the preferences. And here you can see that NSGA2 is significantly preferred by all selected QIs, followed by SPA2 with minor differences. So let's look at the result from another perspective. So here I show a graph, and an arrow means that the tail is the algorithm which was significantly preferred by a QI over second one. For example, you can see that there's an arrow from NSGA2 to CELDE, and the tail is NSGA2, so it means that NSGA2 was significantly preferred over CELDE. Similarly, NSGA2 was also significantly preferred over PAES, and also NSGA2 was significantly preferred over MOSEL algorithm. So we also performed some additional analysis based on some categorization of quality indicators from the literature. So this is the classification that was recently published by Lee and Yao. And here you can see that on the columns you can see different quality indicators, for example C, ED, EP. And in the rows you can see different categorization of quality indicators, for example convergence, spread uniformity, and cardinality. And these are the different characteristics that exist in a particular categorization, and then here they mapped that which characteristics are covered by each quality indicator. So for example, convergence means that how close our solutions are to an ideal or reference Pareto front. And if you look at in terms of convergence, you can see that for example, if we look at C, so C is partially covering convergence. But if you look at, for example, EP, GD, for example EP, HV, and IGD, we can see that they are fully representing convergence, spread, and uniformity, and they are partially covering cardinality classification of characteristics of quality indicators. So now, we map these results into our results from the experiments, and we can see here is that these are the numbers that are we counted, that for example a column in terms of a number. For example, if you look at the NSGA2 column, you can see that for convergence there are 17. This number means that in total 17 comparisons NSGA2 was significantly preferred in terms of convergence over other multi-objective search algorithms. So here if we look at this number, we can see that NSGA2 is the clear winner. So we can see that NSGA2 is significantly preferred by all the selected QIs, followed by SPR2. So let's come to the discussion. So we did all this experiment, we studied 2 research questions. So what is the output for, or what is the key results that for the readers of this paper? So let's discuss that. So our main output from this empirical evaluation is a guide that helps you to select a MOSA for a particular QI before even performing experiments. So if you remember, this is our result table. So what our suggestion is that, let's say you want to select a particular QI, and you know that you want solution based on any particular QI, and you want to correspondingly select one or more multi-objective search algorithm for your problem, for experiment, for instance. So for example, I know that I want solutions which are represented by hypervolume. So based on this table, you can see that I can clearly see that NSGA2 has the highest number here, 3. So it means that for me, I can safely choose NSGA2 here. But if, for example, I want to choose 2 algorithms, so I can select NSGA2 and SPR2 based on this table, because this tells me that there's a quite good chance that NSGA2 and SPR2 will produce the solution which are representing HV characteristics representing by HV quality indicator. This is my preferred option. So if I look at EP, then let's say my preference that I want solutions which are represented by EP. Then in this case, you can see that we have a tie. We can see that NSJ2, SMPSO, SPA2 all have number 2 here. So what shall we do? So one possible option is that you can choose any, because they're all have the same number here. So this could be one option, but there can be another options too. For example, in this case, let's say I wanted to select C, and here you can see that you have a tie here with 2 algorithms, that is NSGA2 and SPA2 with the number 2. So then what shall I do? So another option is that I can look at the C, and I can see that from the second table, C is represented by convergence class of and is represented by convergence. So in terms of convergence, then I have the third table that we created in our based on the results of our experiment. So here you can see that so C is represented by convergence. So then I simply go here, and I see that in this case NSGA2 could be the best option, because it has highest number of number here, which is 17. So it means that I can choose NSGA2 in this particular case. So conclusions and future work. So in this paper, we provided a guide to select a MOSA for SBSE researchers, so that they can choose MOSA that is represented by their QIs of their choice, or the classification of a particular category of a particular QIs, for example, convergence, uniformity, and so on. So in the future, we also want to study characteristics of SBSE problem, because if you look at our results, we didn't study the characteristics of the problems in empirical evaluation. For example, we didn't study the number of objectives, we didn't study the distribution of data of SBSE problems, and so on. And we also didn't study the time performance of MOSA, which could also be another factor can help us to select a MOSAs. And we also want to study more based on the categorization of QI, because if you look at our experiment design, we performed all the experiment based on each individual QI, and later on we mapped the data to the classification of QIs, for example, convergence and so on. So another idea could be to start directly with those categories and repeat the experiment and see how our results look like. And then also we really hope to collect more data and improve our guide, and that's why we have everything available on this link. And if anyone has any results they would like to share, we'll be very happy to keep updating our guide that can be available for everyone. So here I will stop my presentation, and I look forward to questions. And yeah, thank you very much for your time.